Hi all. Very good evening and welcome back to the fifth week of TLI sessions for Artificial Intelligence Search Methods for Problem Solving. So first of all, can you see my screen and is my voice audible? Can anyone just confirm? Okay, thanks for the confirmation. Um, Sorry about that. Yeah, so this week we'll be discussing some questions from week 5 content, which will basically cover the uh, some more methods to find optimal paths, basically branch and bound, uh, A star, and so on such methods. Just give me a moment. Yeah, sorry about that. Um, yeah, so as I was saying, this week we'll be discussing some questions from week 5 content, which will cover methods like branch and bound and A star that we can use to solve different uh, different ways to solve the TSP problem that we are going to that we saw in the lectures. And yeah, without further ado, let's get started. So I won't go into the variations of A star method. Once you understand how to solve A star, it would be fairly simple to extend it to the variations of A star as well. But that is a topic for later discussion. For now, let's get started with the questions for this week. Okay. Okay, so this is the first question in front of you. So consider that there is a map shown over here, which is a map of some fictional country called Triangle Country, and so the circles are the nodes and the edges are the uh, basically the edges connect the different nodes or cities, you can say, and and this is a complete graph. So for those of you who might not be aware of what a complete graph is, it's a graph in which every node is connected to every other node. And if you notice in this particular graph, there are some edges missing. And for all those missing edges, we can assume that uh, the cost of that particular edge is going to be very large. Let's say something like plus 10,000 or 100,000 or something like that. Okay, and just to avoid the clutter in the image, we have not shown such high cost edges or infinite cost edges. Okay, so is the setting clear? Any doubts about the setting of the problem?
No, sir.
Okay, thank you. That's great. So in this question, we are asked that the branch and bound algorithm is about to start looking for a TSP tour or a traveling salesman problem tour, and we have to find what will be the lower bound on the cost of the tour that it will begin with. Okay, so basically we are asked about the lower bound on the cost of the tours. Remember that this is just a lower bound, so the tours can be valid or invalid. Okay, but yeah, I'll let you give some time to the question and you can try to solve it. Um, and then after a couple of minutes, we can have a discussion on the solution. Thanks for your message, Sachin. So I was on mute. That's why I was, so you couldn't hear my voice. So I was just letting you have some time to go through the question and try to solve it. But yeah, it's a nice point to maybe uh, break in and start discussing the solution. So have any of you thought about how we could approach this particular problem? Okay, no worries. Let's start uh, solving it, and uh, maybe you guys will see that you were also heading in the right direction, or you will find yourself corrected, or uh, one of the above. So let's start discussing the solution. So remember that we are asked here about the lower bound on the cost of the tour, uh, and so as I said in the beginning, the hint is that it may or may not be a valid tour. Okay, so if we try to represent this particular map that is given to us in the form of a table, where the rows and the columns are all represented by the different nodes of the graph, uh, it could simplify the problem for us to quite a bit of an extent. Right. So the first thing that we should do is we should name our different nodes with different alphabets so that it will be easier for us to address them. So um, and once we have done that, we will have a table that will look something like this. Okay, so I'm just showing a hypothetical table over here, and then we'll move on to the real table. So let's say that we have the first node as A, B, C, and D are the four nodes in this fictional graph. Uh, and then we have A, B, C, and D. And the cost of going from A to A will be 0, B to B will be 0. So the diagonals will all be 0. And then this will have some or the other cost, something like this. And we can fill in the table entries as is defined by a graph. Okay, so if we apply this technique to our graph, we will have something like this. Okay, so if you can notice over here, we have named all the nodes. So this is our A node, this is our B node, this is C, D, and so on and so forth. And we have also formed a table where we have the distances from A to every other node in the first row, from B to every other node in the second row, and so on and so forth until I. Okay. Now, when we want to find the lower bound, what we can do is we can consider one row at a time. Okay, let's say we consider the first row, and we can look for the minimum two edges or cost of the edges that are linked to that particular node. Okay, so for example, we consider the A node, and we see that we have 14 and 12 over here with the which are the two minimum cost edges linked to A, and the third one is 55, which is greater, so we ignore that for now, right? So we take these two values and we add them up. That gives us the first part of our solution. We repeat the same for all the different nodes. Okay, so for if we do it for B, if we do the same thing for B, can anyone tell me what will be the two weights that we are going to consider? 12 and 10. That's right. So we will consider 12 and 10. And if we sum these two up, we will get 22, which is the second part of our solution. And we'll repeat this for all the rows. which basically means for all the nodes, and we'll have this particular set of values. Now what we can do is we can sum these up, and whatever sum we get, we can divide it by 2 to get the lower bound. Now, why we need to divide by 2 is because we might have edges that are repeated in this sum. Okay, for example, from A, we consider this A to B edge with the 12 cost. Again, from B, we consider this 12 edge, right? Which is B to A in this case. But this A to B edge was repeated twice. Similarly, there might be other edges as well who are which are repeated twice in this summation. And so we need to divide it by 2 to get an estimate of the lower bound. Remember that this may or may not be a valid tour. Okay, but this is the lower bound, which means that the cost of any tour cannot go lower than this particular value. Okay, so any doubts on this question? Okay. Okay, just to address one of the queries in the chat, how can we convert a edge tour to a graph or a tree? So what you can do is you can start from a particular node and then see what are the different directions you could go through or go from that node through the edges. Okay, so let's say we have something like this A node over here. Okay, so from A you could go to either I or C or B, right, with different costs of the door of the different edges. So those could be the children of your node that you're starting from. Then again, from each of those individual child nodes you could further branch into the nodes that you could go from those child nodes, right? And that's how you can convert your edge tour to a graphical structure or a tree structure. I hope that addresses your question. Uh, if not, let me know. And we'll actually see something like that. We will convert a huge graph that we are going to see in some of the coming questions, and we are going to convert it to different search trees uh, while we try to solve the branch and bound and A star algorithms. Okay. Uh, Yeah, so we will actually go through a very elaborate example. So we will go through the whole process, so don't worry. Um, okay, so there's another request to go through the lower bound example once more. So basically, what the question asks is, the branch and bound algorithm is about to start looking for a TSP tour. Okay, what will be the lower bound on the cost of the tour that it will begin with? So this basically means that. Um, what we have to do is we have to start from, or we have to consider each node at a time and look at the least cost edges going from or connected to that particular node. Okay, so for example, for A, the least cost edges are 12 and 14. Of course, we won't consider the zero value over here, and that is because we don't want to keep going from the same node to the one node to the same node, right? So this zero is not really what we are going to consider. We are going to consider the two minimum non-zero values or entries in each of the rows, and we are going to sum them up for each node. Okay, and once we have those values for each of the nodes, we are going to sum over all of these individual sums and then divide them by 2. Why we are dividing by 2 is just to avoid repetition of edges twice, because for some of these instances one edge may have been counted twice while considering two adjacent nodes or vertices, right? So if you just sum these up and divide the sum by 2, you'll get 108, which is the lower bound. Okay, so this was the lower bound. Let's check the answer. It is 108. Now we move on to from the lower bound to an optimal tour. Okay, now this is a small graph and a small map, so we can actually try to solve this by hand and try to find an optimal tour for the above problem, this TSP problem in this particular map or graph. Okay, so you can feel free to start from any of these nodes and try to find a tour that goes through all of the vertices and at the same time has the lowest cost. Okay. Uh, Good question, Ram. So we are taking only two edges because when we are trying to construct a tour, each node can be connected to two edges at once, right? We are trying to find a tour through the graph, right? So in that final tour that we are going to get, each of these nodes will be connected to two edges. That's why we are considering two edges. Okay, so we already have an answer to this question in the chat box, but I'll give a few more minutes so that the others can also try it out, and then we can discuss the solution. Okay, so we have a couple of answers. Now let's try to find the optimal tour and see for ourselves which of these, what is the correct value of the cost of the optimal tour. Okay, so for now, just ignore uh, this part of the slide. Okay, for now, just ignore this. We are just going to focus on this map part and this table part. Okay, so let me just clear out the writings so that we can solve it. Okay, so suppose we start from this A node over here. Okay, for our convenience, we are starting from this A node. So we are at this node and we have to choose which direction we could go into from A. Okay, so what do you think? In order to construct an optimal tour, which direction or which node will we go to from A? Will it be this 12 cost edge from A to B? Will it be that 14 cost edge from A to C or 55 cost edge from A to I? B, yeah, right. We'll go from A to B, fine. So we went from A to B and we added 12 to our to added cost 12 to our tour. Okay, so now we are at B. Now when we are at B, we have only one option, right? We can only take this 10 cost edge and go to C because we don't want to go back to A. That will be against the rules of the TSP problem, right? So we will take this 10 cost edge and we will go to C, and let's add 10 to our optimal tour as well. Now we are at C, and C has two possible uh, or one of the possible. So it can take either this 14 cost edge or this 77 cost edge, but as per our constraints of the TSP problem, what do you think, which edge do you think would we take from C? D, that's right. We will take the edge to D, and the reason behind that is that we can't go from C to B, although it has the least cost, because B has already been covered in our tour. We also can't go from C to A because A has already been covered in the tour. And even though the cost of C to D is 77, which is the highest of the cost of the edges connected to C, we are still going to take the node from C to D and go to D. And we are going to add 77 to our cost. Okay, now we are at D. Now what do you think? Which edge are we going to take? Is it going to be the 10 cost edge to F, or is it going to be the 14 cost edge to E? Okay, so some of you are saying that it will be E, some of you are saying that it will be F. So think about it. If we actually go from D to F, okay, even though this looks like a very lucrative direction to go into, it has the least cost edge of cost 10 going from D to F. Once you are at F, right, you can either go to E or G, okay, and E has the lower cost over here. So if you go from F to E, you will be stuck over there, right? Because you can't go back to D, you can't go back to F, and you will be stuck over there. And if you want to cover the rest of the nodes, you will have to go back to F, which again violates the constraints of the traveling salesman problem, right? So even though 14 is not the least cost edge over here, we are still going to take the 14 edge from D to E. Okay. Now when we are at E, we have to take the 12 cost edge to F. Okay, so I didn't add these. So 14 plus 12. And then we are going to take 92 to G. Then we are going to take 10 and 14 and then back to A. Okay, so let me shift to the next slide. Right, so if we just add up all the values that we just noted down, the first edge we took was A to B, which was of cost 12. Then we took B to C, which was of cost 10. Then we took C to D, which was of cost 77. Then we took D to E, which was of cost 14. Then we took E to F, which was of cost 12. Then F to G, which was of cost 92. Then G to H with 10, H to I with 14, and finally I to A, back to A where we started from, of cost 55. And if you sum all these up, the total cost would come up to be 296. And this is the optimal tour in this particular graph. Okay, and since this was a simple graph, we were able to solve it by hand, but that might not always be true for very large graphs. Okay, but for the sake of understanding how uh, we should go about thinking about these uh, optimal tours, this was a helpful example, I hope. Okay, so the previous question, you mean the lower bound one, right? Okay, so I'll just quickly go through it once more. So if you remember, here what we are doing is we are not simply when we are at a particular node, we are not simply being greedy and choosing to go via the edge that gives us the least cost. Okay, for example, when we were at C, we didn't choose to go back to B via this 10 edge, or when we were at D, we did not choose to go to F via this 10 edge. We instead chose to go to E via this 14 edge, even though this was not the minimal cost edge. And this is why this is the optimal tour, right? Uh, on the other hand, in the lower bound tour, we don't care about whether the tour is optimal or not. Okay, we just see what are the two minimum cost edges associated with a particular node, and we just consider those two as part of our tour. Okay, and that is what makes the lower bound different from the optimal cost of a particular tour. I hope that clarifies your doubt. Let's quickly check the answer. And yeah, the cost of our optimal tour for the above problem is 296. All right. Any doubts on this question, or should we move ahead? Okay, that's great. Then let's move ahead to the third question, or the upcoming question. So here is the big graph that we are going to deal with in the upcoming questions. Okay, so this is the same graph from if you remember, in the previous sessions, we considered the Manhattan distance. Okay, we calculated the Manhattan distance of various of these nodes. Okay, it's the same graph, but the difference, the big difference over here is that these costs or these values that are shown on top of each of these edges or on beside each edge, right? These are the actual costs of going from one node to another, not the Manhattan or the heuristic or different any other heuristic. It is the actual cost of going from one given node to another given node. Okay, and why we have given this is it's going to become clear in a moment, but I just wanted to put this out so that there's no confusion in the upcoming questions. Okay, so now that we have that out of the way, let's move on to the question. And okay, some more background on the setting of the problem. So basically, I'll just go through this information. So the figure over here shows a map with several locations on a grid where each of the tile is 10 cross 10 units in size. Okay, so like I said in the previous um, session also, this each of these small square boxes is the 10 cross 10 unit dimension box. Okay, and S is the start node, the node marked with red over here, and G is our goal node. And the locations are connected by bidirectional edges or roads, and each edge has a cost associated with it that is the same in both directions. Okay. Another assumption is that the move gen function for this particular problem or graph returns nodes in alphabetical order. So this will be useful while we solve or go through the steps of the BNB branch and bound and A star algorithms. Uh, and when several nodes have the same cost, we will use the alphabetical order to break the ties. Also, when the same node occurs multiple times with the same cost, but then we use the open sequence number to break the ties. That is, we refine the nodes that occur in the node occurrence that is the oldest or was placed earliest in the open list. Okay, so this might seem like a bit of a jargon right now, but as we go through the steps, this will become clearer. And again, we use Manhattan distance as the heuristic function. Okay, so not to confuse this with what I just said a few minutes ago, we are still going to use Manhattan distance in our algorithms, but the costs that are shown over here in this graph are the actual costs and not the Manhattan distance that we calculated the previous time. Okay, with that out of the way, the question over here is that we will use a variation of the branch and bound method, which is the simple branch and bound algorithm covered in the video lectures, and this particular method allows for cyclic refinements. Okay, so refinements, in case if any of you had any doubts, refinement is basically exploration of a particular node. So if you say that we are refining node S, we mean that we are exploring the node S and looking at what are the possible options we could move ahead from this particular node. Okay, that is basically called refinement. And cyclic refinements basically means that this particular algorithm allows you to come back to a node that you had started from, okay, in order to find the tour. So for example, when we construct the search tree for this graph, uh, we are allowed to go back to the node that is its parent. Okay, let me just draw it actually to make things clearer for you. Okay, so in order to establish some jargon or some format in the solution that we're going to follow, so we're going to convert this big graph that we saw over here, okay, this one, into a search tree using this branch and bound method, one variation, the first variation of this branch and bound method. Okay, and so we are going to start with this S node. Okay, so there will be, so we'll be representing each of these nodes with a box, and each of this box will be having three values or three fields. One will be the name of the node. Okay, so we are starting from the name of the node. Okay, then we are going to indicate the order in which this particular node was refined or inspected or explored. Okay, so since we are starting with the start node, which is S, this will be the first node that was inspected. That's why it has an number 1 as the sequence number. And then the third field over here will be the cost associated with the partial tour till now. Okay, so when I say partial tour, I basically mean that, let's say you have a node, you went from this node to another node, then you went from this node to another node. So the total cost, let's say this is X, this is Y, and you still haven't reached your goal node. Okay, so this is only a part of the solution, but the actual cost of starting from your initial node S and going up till this particular intermediate position in your solution, the total cost up to that point would be X plus Y, right? So that is what you're going to put in as the third field in your box. It will become clearer as I draw the children of this particular S node. So let me just go ahead and draw that. Okay, so let us go back to our graph and see what are the nodes that we could go to from S. Okay, so from S we could go to E with cost 40. We could go to J with cost 30, we could go to O with cost 60, and we could go to K with cost 60. Okay, so let's write all this down. So we could go to node E with cost 40. Okay, I'm not writing the sequence number as of now because we have not decided which node we are going to inspect next. Then we could also go from S to J with cost 30, or we could go to K with cost 60, or we could go to O again with cost 60. Okay, so simply based on this, which of these options do you think would be the most fruitful to explore? J. That's right. We're going to explore J because it has the lowest cost, which is 30, which seems the most promising as of now. Okay, we're not saying that this will go to be the ultimate part of our final optimal tour, but as of now, as of this point of time, it seems to be the best option to us. So we're going to go ahead with it. Okay, before that, just to address a few questions. No, it is not necessarily a Euclidean distance. The costs mentioned in the big graph, they are just some random distances assigned to the different edges, random costs assigned to the different edges. Also, is heuristic function only a value or includes both Manhattan and heuristic value? No. So we are right now talking about the branch and bound method. Okay, when we go to the A star method, then we are going to consider a combination of the actual cost and the heuristic value. But as of now, you don't need to worry about it. As of now, we just need to concern ourselves with the actual cost that are given in the big graph. Okay, so we are going to consider J. So let's write sequence 2 over here. Okay, now let's see what are the different children or different places we could go to from J. Let's go back to our big graph. Okay, so this is where J is. Okay, and from J we could go to A with cost 60, we could go to N with cost 40, we can also go back to S with cost 30. Okay, so this is what I mean by cyclic refinements. We can go from S to J and then back from J to S as well in the search tree that we are constructing. So let's write down our options. So from J we could go to A with cost. So remember that this is the total cost of the partial tour. Okay, so even though the cost from J to A is 60, we are going to have to consider the cost from S to J to A, right? So this will be 30 plus 60, which is 90. So the cost of going from S to J was 30, then the cost of going from J to A is 60. So the total cost up till this point will be 90. Similarly, we could also go from J to N with total cost 70. Or we could go back to S with total cost 60. Okay, so let us mark this S node with green to say that we have already refined this particular node and this J also. Now, whatever the nodes in the graph that we have that have not been refined or not been explored as of now, we are going to consider all such nodes. Okay, so we are also going to consider E, we are going to consider A, N, S, K, and O. What this basically means that we are going to consider different possible paths to start with. Okay, so basically this SE part over here, this edge from S to E indicates that we are exploring this SE partial path. This SJA basically explains that we are exploring this SJA partial path and so on and so forth. So we are not restricted by the node that we are at currently, right? We can explore any of these paths and we can switch back to any of these paths at any moment. So as of now, from the available options, what do you think would we jump back to? E, that is right. Okay. What is it? So before going on to with further explanation, I'll just address a few simple queries in the chat. So the difference between A star and best first search, when we go through A star, I think the difference will become clearer to you. Uh, what would be open and close for this? So for that, I would refer you to the actual pseudocode or the algorithm for each of these methods that must be there in the lecture notes by Bhaskar sir. So I encourage you to check that out. And if you can, if you're comfortable with programming, you can even try to implement this particular algorithm, and that will be a really good way to understand it well. But as of now, I'm going to continue with this visual aid of drawing the search tree uh, because that is easier to I personally feel that's easier to explain and also to understand, but and also to use in an exam. But yeah, you can always go back to the algorithm and look at the data structures and the uh, uh, open and closed lists used over there. Okay, so coming back to our graph, we are going to consider this E node now. So we are going to mark the sequence number as 3, and we have also explored this. So now we are going to add the children of E. Okay, so the children of E over here could be A, B, F, and S again. Okay, so there will be 1, 2, 3, 4 children of E. And since there is very less space over here, let me actually just shift to the whole search tree that I've already drawn, and we can go through each of these in detail. Okay, so if you remember, we started with our S node, okay, which had a cost 0 and which had a sequence number of 1. Then um, yeah, so this S had 4 possible directions it could go into. It could either go to J or to E or to K or to O, and we chose to go to J because that looked like the most promising solution at that particular point of time. Okay, and so we were at J. Then we saw what are the possible options we could go to from among the options that are available to us, and we saw that E is the best looking option at the moment, so we jump back to E. Okay, so we had seen this until this point in our previous explanation, and once we explore this further, draw further 4 children of E, we will see that the best looking option now is K. Okay, so we will mark K as sequence 4 and we are going to draw its children, and then we are going to see that O is the best looking option, so we're going to jump back to O, and then we'll draw all its children. So one of this is missing, I think, but you can complete the diagram, and we are going to proceed in a similar manner until we finally reach uh, okay, so we have not shown the complete search tree over here. We have just shown the partial search tree because the question asked us to find the 5 nodes that were inspected from index 6 to 10th. Okay, so what this basically means is that um, the first node that was inspected was S, right? So S would have index 1. Second node that was inspected was J, so it will have index 2. Third node that was inspected was E, so it will have index 3, so on and so forth. Then we will have K with 4, we will have O with 5, then we will have S with 6, okay, this one. Then we will have N with 7, then again S with 8. Okay, so remember that this S and this S is different. Okay, so this S is coming from SJS, whereas this S is coming from SES. So 8 again, then A with index 9, and then J with index 10. Okay, so this search tree could go on expanding further unless we reach at our goal node through one of these branches. And but the question simply asks us what are the uh, 6th to 10th node that we inspected, and that will be these SNSAJ nodes, right? So that is what is asked in this question, and that's why we have shown this partial search tree over here. And the 5 nodes from the 6th to 10th nodes that were refined or inspected by this particular variation of the branch and bound method are SNS, A, and J, as we saw in the search tree. Yes, Rocky, the path would repeat because we are allowing for cyclic refinements, right? So this would have a repetition of going from one node to another node. In the coming question, we'll see another variation of this branch and bound method where we do not allow cyclic refinements. So in that case, repetition will not be allowed. But I'll show this search tree once more, and then I'll leave it over here so that you can convince yourselves, go through this search tree and convince yourselves about the solution before we move on to the next question. Okay, Yeah, there was a hand raise. You can feel free to speak up. Okay, I guess it was by mistake. So yeah, I'll leave the solution in on for a couple of minutes, and then we can move on to the next solution. In the next question, which will basically be the same branch and bound method, but with the restriction that I was talking about here in the next question, we won't allow cyclic refinements, right? So our search tree would be looking slightly different. So those of you who are already convinced about the solution, this particular solution, they can think about how the search tree would look like in the next question when cyclic refinements are not allowed, and then we can come back to that solution after a couple of minutes. Okay, so there are a couple of doubts in the chat which I will quickly address. Um, can you maybe mute yourself if you don't have a question? Thanks. Okay, okay. So the first is why the sixth node is not in. So if you look at the search tree, okay, uh, this particular field over here that we saw in the format, this indicates the sequence number in which it was inspected, right? And if you see that, so the first node that was inspected was or refined was S, this particular node. Then we refined J, then we refined E, then K, then O, and then we refined S. Okay, so this was the sixth node that we refined, and that's why S is 6 and not N. N is the seventh node that we refined. Okay. Okay, and then the next doubt is in this example, E is not the child of J. So how do we choose E? So good question. Again, the reason we were able to choose E even though J is not a child of it is not a child of J is because we are looking at all possible available options at a particular moment. Okay, not just at the children of the node that we are currently exploring or refining. We are exploring all possible options that were there from the previous nodes that we refined and did not and chose not to explore the children of that particular node, and also the children of the particular node that we are currently refining. Okay, so yeah, as one of you mentioned, it checks all the open nodes. Okay. Okay, so we already have another a solution in the chat for the case when cyclic refinements would not be allowed. That's very good. Um, so if there are no doubts in this question, we can then move on to the next one. Shall we move on to the next question then? Okay, great. So, okay, one partial question before this. Okay, so we just saw these SNSAJ nodes, right? So this question basically asks the cost of these nodes the associated cost of these 5 nodes that we just saw, and you can just quickly refer back to the search tree and see that this cost would be 60, 70, 80, 90, and 90. Okay, so sorry about that, I had not shared this solution. Yes, I was just talking about this partial question in the middle, which basically asks us to list the cost associated with all these 5 nodes that we just found out in the previous question. And if you just quickly check the search tree, it will be 60, 70, 80, 90, and 90. Okay, so I won't go into the details. You can just quickly verify it on your own. Let's move on to the second variation of branch and bound that we were talking about, where we prevent cyclic refinements. Okay, uh, can you maybe mute yourself? Uh, okay, thanks. Okay, so yeah, it does not refine the nodes that are already present in the partial path from the root to the current node, and therefore it keeps the each partial path in the search free tree free of duplicate nodes. Okay, so there will no this so they, we won't have partial paths like SE, SE, SES. Okay, so there won't be repetitions. Otherwise, the whole algorithm remains the same, and we are again asked to return the 6th to 10th nodes that we are going to refine or inspect or explore. Okay, so the search tree for that case would be differing from this one in what way? So the first level of the tree would still be the same. We would still have S in the first level. We would still have E, J, K, and O in the second level. But when we go to explore this jth node, right, we won't have this particular node S because the cyclic refinements were disallowed or prevented. So we will only have A and N. Okay, let's quickly. Okay, I'm sorry, I wasn't again sharing the screen. So let me just quickly go over here. Yeah, so what I was saying is this part of the tree will still remain the same. We will start from S. There are 4 possible directions we could go to: E, J, K, and O. That will still remain the same in the next search tree for B and B2. But when we are uh, writing the children of this particular J node, remember that in this BNB1 method, we also wrote this S node. This won't be there in BNB2 search tree. So the children of J will only be A and N. And similarly, the same applies for all the other nodes as well. So here also we won't have S, and so on and so forth. Here we won't have E. Okay, so let's go to the search tree for the PNB2 method, and you can see that this is a slightly smaller reduced search tree. Okay, so here also we start with S, okay, with cost 0, index 1. Then we choose to explore J because that is the best looking option with index 2 and cost 30. Now here, as I told you, there are only 2 children of J, A and N. Now from among all the options available at this particular instant of time, we find that E is the most best looking option. So we go for E now with sequence 3 and cost 40, and then we write down the children of E, and then you again notice that we don't have any S node over here. Okay, so this is not here because cyclic refinements were not allowed. Similarly, after we have drawn the children of E, we will see that K is the best looking option, so we will explore K, then we will explore O, then N, A, 8, F, 9, and sorry, N and L. So if we draw the or if we write down the order in which the nodes were inspected, like we did in the previous instance, it would be something like this. Okay, so first we inspected S, then we inspected J, then we inspected E. then we inspected K, then we inspected O. Okay, by the way, so when we were at this point of time, right, when we were done with inspecting E and we were looking at whether we should explore this K or O option, why do you think we chose to explore K before O? Can anyone tell me? That's right, alphabetical order. So this is where our assumption at the start of the problem statement comes to use, because alphabetically K occurs before O, so we are choosing to explore K before O. So just a minor point that I wanted to mention. Okay, so after O, we explore N, which is 6. Then we explore A, which is 7. Then we explore F, which is 8. Then N, which is 9. And then L, which is 10. So here the 6th to 10th nodes would be N, A, F, N, and L. So this will be your answer, N, A, F, N, L. Okay. No, no, no. Okay, no, okay. So I guess some of you are confused about the cyclic refinement prevention of it. So this is not a tour that we are following. Okay, this NAFNL or this whole sequence SJEKONAFNL, this is not the tour that we are finding. This is just the order in which we inspected or refined the different nodes, right? So this N is differing from this N. This N and this N are not same. They are different. How they are different? Let's see that. So this particular N, which we inspected at instance 6, this is the result of the tour S to J to N. Okay, so this particular thing gives you the tour, not this thing. Similarly, this N that we inspected at the 9 sequence, this is a result of the tour S to O to N. So this is how these two N are differing. Okay, cyclic refinements are still disallowed in this case. If you see that any child of a particular node doesn't have that particular node repeated, you won't find S anywhere in any of the child nodes over here. You won't find K in any of the children of K. You won't find N in any of the children of N. Okay, so does that help your query on why we have N 2 times in the answer? Okay, sure. Let's go over it from start. Let me just wipe out everything. So one key thing to remember over here is that what we are asked in the question is the order in which the different nodes were inspected. Okay, and one node can be inspected multiple times in the graph, in the big graph. Okay, but here what we are constructing is a search tree. Okay, and each of the branches of the search trees gives us a partial solution. Okay, so for example, this particular branch, if you follow this gives you a path from S to J to N to O. Okay, so this is one particular partial solution with a total cost of 110. Similarly, there is another partial solution that is represented by another branch of the search tree. Let's consider this particular branch. We go from S to O to N to T with a total cost of 150. Okay, so each of these branches are giving you the partial solutions, right? So in each of these branches, you will notice that there is no node that has been repeated twice because we are preventing this cyclic refinements. But the order in which the nodes are inspected that can have a repetition of the nodes, right? Because you started from S, okay, then you explored J, then you explored E, then you explored K, then you explored O, then you explored N. Okay, so this N, for the first time that you are inspecting this N, you are considering this partial solution from S to J to N. And when you are considering after this, you move to A, okay, then you move to F, and then you move to N. And when you are considering this N, this is a part of a different partial solution, which is from S to O to N. Okay, so it's not like you start from a node, you go in a certain direction and you get stuck at that. No, no, you are exploring all the different partial solutions that you could uh, go to or take from a particular starting point. Okay, so that is why the order in which the nodes have been inspected can be repeated, can have a repetition, but the partial solutions will not have any repetitions. If you compare this with the previous example that we saw, so if you notice, this will have a repetition of elements in the partial solution itself. Okay, you have S to J, then again to S, and then again to J, right? So this has a repetition is Sj itself, whereas this BNB2 method does not have any repetition in the partial solutions. Okay, so you see the partial solutions in both cases, but the difference between in BNB2 and BNB1 is that in BNB1 your partial solutions will have repetitions, whereas in BNB2 your partial solutions will not have repetitions. Okay. One other query was if the second n cost is 70, then we cannot repeat it. Uh, so if the cost had been different, then if the cost had been the cost of the second n had been something like 70, uh, then even at the beginning instance we could have chosen that particular solution, right? What I think what you're meaning to say is that if this had been 70, whether you would have chosen this one or this one. That's what you mean to ask, right, Vanshika? Yeah, okay, that's a good question actually. So if you see that O was the fifth node that we inspected, right? And if you consider the different options available to us at this point of time, you would also have this in the open list and you would also have this in the open list. And since both of these have cost 70, you could have randomly chosen any of them and then moved ahead and saw, and you could have later seen that. No, actually, not that is not the case. I'm wrong about that. So if you remember one of the assumptions that we made at the start of the map when we discussed the problem setting. Let me just go back to that. Huh. So uh, when the same node occurs multiple times with the same cost, then we use the node that the that was appearing that is the oldest in terms of timestamps. Okay, so if I connect this back to our solution over here, this n was added when j was refined. Okay, and j was refined second, right? So this n would have a place in the open list much before than this n, because this n was added when we refined o, and o was refined much after j was refined. Okay, j was refined second, o was refined n. So in a sense you could say that this n is older than this n. So that's why you will choose to go with this n, even if this cost was 70. Does that answer your query, Vanshika? Okay, that's great. So once again, I will remove this clutter and I'll keep the solution here for a while so that you can go through it and convince yourselves about the BNB2 search tree, and then we can then move on to the next few questions of the next few questions and the algorithms that we're going to explore.
Sir,
Yeah,
I have a doubt, sir.
yeah, please go ahead.
Sir, suppose if the path is like S, J, N, and so on.
Okay.
So if they have asked the cost of the path, should we
Mhm.
add this 0, 30, 70, or the actual cost given in the graph?
No, you don't need to add it because you are already adding it when you are mentioning this 30, 70, and so on and so forth, right? So
Yes, sir.
if you look at this individual cost in each of these nodes, let me use a different color maybe. So this cost represents the cost of going from the start node or the root node up until this point. Okay, so this basically means the cost of going from S to J, which is 30. This 70 means the cost of going from S to J to N, which is 30 plus 40, 70. And this 120 represents the cost of going from S to J to N to T, which is 30 plus 70 plus 50.
Then the cost of the goal node would be the cost of the path. Am
Exactly.
I correct?
Yeah,
Yeah.
exactly.
Okay, sir. Got it. Thank you.
Yeah. Also a good question. So thank you for all the questions that you are asking. That is also helping me cover some points that I otherwise would have forgotten. So the presentation slides are already available in the drive folder. If you want, I can upload this Jamboard file as well towards the end of the live session. Okay, fine. I will upload the Jamboard slides as well. Okay, so any further doubts on this particular solution, the branch and bound version 2? Okay, great. Also, I hope that by this point we have addressed one of the queries that was raised towards the starting of the session on how we can build search trees from big graphs. So I hope that is addressed. Okay, that's great. Um, so now let's move on to the next question. Okay, before that, let's just quickly check the solution, which was NAFNL, right? Which we just saw through the BNB2 search tree. Now we are going to move on to the A star method. Okay, so up until this point, what we were doing is we were considering the actual cost from the big graph, right? Now in A star, what we are going to do is we are going to choose a combination of the actual cost and a estimated cost. So let me just explain a small intuition behind it. Okay, suppose this is your start node. Okay, suppose you have already found some partial solution in the graph up until this point. So this is where you currently are. Let me just mark it with a plus sign. Okay, and I'll just draw a rough boundary. Okay, so you can say this is your rough boundary. And when I say boundary, I basically means that uh, this is your goal node. This is where you want to reach. And you have covered this partial solution up until this point. Okay. And you are yet to explore this particular area of the graph. Okay, you have not explored this area of the graph. You have already explored, let's say, this particular area of the graph, and you have found the optimal partial solution up until this point, which is this particular path. Okay, so you will have an actual cost associated with this particular path, right? Let's call that G. And we will also have an estimated cost of going from this particular plus node to the goal node. And how we will have that estimated path? For that, we can use the Manhattan distance, which we will call as the heuristic H. Okay, and now we will define the cost of that we are going to deal with in the A star method as a combination of this G and H. Okay, so if you remember, let me just use another white slide. When we were drawing the search tree in case of branch and bound, we were mentioning S, we were mentioning 1 as the first index of the node, that is the first index that is indexed, that is inspected, sorry, and we were mentioning the cost as 0. This will no longer be the case, because in this case, this cost would be a function of G plus H. Okay, so G in this case is 0. Okay, the cost of going from S to itself is 0, but the estimated cost of going from S to the goal node, that will be decided by the Manhattan distance. Okay, and for that we have to revisit our big map or big graph, and we have to calculate the Manhattan distance between S and J, S and G, or the goal node, right? And that would be H. So let's say that is something like 160. Okay, I'm not sure if that is actually the case. You can verify it, but I'm just assuming. So our cost mentioned here in that case would be 160. Similarly, when we write down the children of S, they were E, J, K. Let me just erase this. And O. Okay. So what each of these parts represents is a partial solution, as I mentioned, right? So when you consider this particular edge from S to E, which basically means that you already know the actual cost of going from S to E from our big map, which is S to E is 40, right? So for this one, G will be 40, and your H will be the Manhattan distance between E and your goal node. Okay, let's see what that is. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so 170 would be the Manhattan distance, because if you remember, each of the small boxes was of 10 cross 10 units in dimension. So your cost would here be 170 plus 40, which is 210. Okay, so the costs of each of these nodes would be changing accordingly by using this F is equal to G plus H formula. This is one of the major differences between um, BNB and A star methods. And another major difference is that we also incorporate something called as propagate improvement. Okay, what I basically mean to say over there is that um, let me just erase all this, and let's say we have some particular node. Okay, this has some children, some child. Let's say this cost is 10. Okay, this cost is 20. Let's call this as A, this is B, this is C. This cost is, let's say 30. Okay, and let's say this cost is 15. Okay, now let's say um, you can go from A to B to D again, or you can, let's say that you can go from A to D to B again, but the cost till this point is, let's say, only 17. Okay, so you see that this particular partial solution offers a path up till B that has a lesser cost than the partial solution that this particular than the cost that this partial solution offers, right? So what we are going to do is we are going to use this information to exclude this particular partial path from further exploration or further analysis. That is what is meant by propagation improvement. uh, but it will become clearer as we discuss the full solution of the A star method. um, Also, for those of you who said that you had a brief network issue, I'll just go over what I just said. Basically, in A star, there are two major differences from BNB method that we just saw. So in BNB, we're only considering the actual costs. In A star, what we're going to consider is the mixture of the actual cost and the estimated cost. Suppose this is a start node and you have found some actual path. Okay, this is the one intermediate node up until some intermediate point. This is the intermediate point. Okay, and you are yet to reach your goal node. So you know the actual cost of this particular part of your solution, let's call that G, and you can estimate the cost of this part of your solution, let's call that H. For that you can use Manhattan distance, and then you will use this G plus H to fill in the cost of each of these partial solutions when you construct a search tree, instead of just using the actual cost. So what this basically does is, the intuition behind this is, it while it also gives you information on the actual cost up until this point, it also gives you information on the estimated cost that you're going to take in the future solutions, the future extensions of your partial solutions, right? So this is more informative than the branch and bound uh, method in a way. And the other difference between A star and the other method that we just saw is propagate improvement. So basically, that what that means is that if we have found some partial solution, let's say with a certain cost X, okay, and then later down the line we find some another partial path that leads us to the same node with a cost Y that is lesser than X. In that case, we will exclude this particular partial path from further exploration. Okay, that is called propagate improvement. Um, but I will now shift back to this particular question, and I will give you some time to try to solve the A star algorithm on your own first, and then we will discuss the solution in detail. Okay, so I'll give you a couple of minutes while I will just go and have some water. Okay, has anyone found some partial answer to this question? If so, you can feel free to write your answers in the chat box. And after a few more minutes, we can go through the whole solution. Okay, so we have one answer in the chat. That's great. What about the others? Okay, we have another answer. That's also good. Okay, let's wait for one more minute and then we'll discuss the solution. Okay, so let's go to the solution now. Okay, so this is our A star search tree. And if you also notice, it has already found out the goal node as well. Okay, whereas a similar size search tree in branch and bound were not able to reach the goal node. So let's go over the solution step by step. Okay, so let's also maintain a list of the nodes that we can inspect at a particular point of time. Okay, that will be easier for us to follow then. Okay, so we start with node S, okay, as usual, which is our first indexed node to be refined, and that has cost 160, which is because it has an actual cost of 0 and an estimated cost of 160, which comes from the Manhattan distance. Okay, and the children of S are E, J, K, and O, right? So out of E, J, K, and O, the most promising looking solution is which one? Okay, E has cost 210, J has cost 220, K has cost 180, and O has cost 180. So again, because appears alphabetically before O, we are choosing to explore K next, right? So K has children now, F, H, L, Q. Okay, so for the time being, ignore this red cross mark given on this H and Q. Okay, I'll come to that. So K has children F, H, L, and Q. Okay, Out of these, so now the possible options are E with cost 210, J with cost 220, F with cost 250, H with cost 270, L with cost 190, Q with cost 210, and O with cost 180. Out of all these, O is the best looking option, right? So we are going to expand or refine O next. Again, O has three possible children, N with cost 260, Q with cost 200, and U with cost 260, right? So again, from amongst all these, the lowest looking cost is that of L, right? With cost 190. So we're going to refine L next. And when you refine L, you encounter this H over here with cost 260, right? And this cost through this partial solution from S to K to L to H, okay, this partial path has cost 260, whereas this other partial path from S to K to directly H, this has cost 270, okay. And since this other partial path has a lower cost than this initial partial path we just found, we will mark this H with a cross, okay. This old H we will mark with a cross, this red cross that you see over here, right? This one, this basically means that this particular partial solution is not worth exploring further, okay. So when we are going to go to the next step of the algorithm, we are not going to consider this H in our possible uh, options that we could refine or explore. And this is what is meant by propagation improvement, okay. Is there any doubt until this point? Okay, that's great. uh, so let's just continue with our solution. And we see that now we have marked H with a cross sign, so we're not going to consider that anymore. um, so now the available options to us are this EJ, um, we have this F, we won't consider H, we have this H, we have, yeah, so these are our possible options that we could consider, right? And from amongst these, the best looking option is which one? This Q, right, with cost 200, which is lesser than all the other nodes, right? So we are going to define Q next, okay, and we are going to draw two children with cost 230 and 290, which is R and W. And then from amongst all these, E has the best looking cost, best looking solution, which best looking partial solution with cost 210. So we are going to add A and B, okay. Again, this cross will come at a later point of time, okay. So as of now we are considering this A, B, J, F, H, Q, N, U, this H, R, W, okay. And amongst all of these ones, J has the lowest looking cost. Okay. This Q was also crossed out when we added the children to this O node, because this has a 200 cost, whereas this has a 210 cost. So this is also removed because of propagation improvement. Okay. Yeah, sorry about that. I forgot to add that. Okay. So now uh, we add the children of J as well, which is A with cost 310 and N with cost 380. And again, we see that this A with cost 310 is lesser than this A with cost 350. So again, we cross this out as well. Okay, so this A is also removed from further exploration. And we proceed in a similar manner, and ultimately we see that following a certain path, which is this path, which is from S to K to L, no, not this path, it's actually S to O to Q to R to V to G. this is our optimal path that we have found from the start node to the goal node with cost 290. Okay, so I'll erase everything again and I'll let you go through the whole search tree once more to convince yourselves that this is the actual solution and the optimal solution as well. Okay, so the answer to the question in that we were initially pointing to, which was the 5 nodes from 6th to 10th nodes that were defined by A star method, those are, as per this search tree that we just drew, those are going to be E, J, N. So E has index 6, J has index 7, N has index 8. Then we have R, and where is 10? F. So E, J, N, R, F are the nodes from 6th to 10th that we have refined. That is also the solution given here. This one. Okay. So yeah, I'll erase this once more and I'll let you go through this search tree so that you can convince yourselves. Any doubts about A star method, about the A star method and the different steps that we just saw? Okay. If there are no doubts, that's great. Um, okay, so there's one request by Rocky to discuss Dijkstra's algorithm, and once again, unfortunately, it would have been better if you could have posted it in the live session, right? So in not so not sorry in the live session in the discussion forum, because I will have to revisit Dijkstra's algorithm to in order to discuss it. But let me try. Okay, you have the pseudo code and everything given over here, and yeah, the Dijkstra's algorithm to find the shortest path between A and B. It picks the unvisited vertex with the lowest distance, calculate the distance through it to each unvisited neighbor, and updates the neighbor's distance if smaller. Let's zoom into this. Okay, so it's starting with A, it's going to 7, then it's going to this one. I will have to revisit the detailed steps of Jigsaw in order to explain it better, Rocky. Unfortunately, I'm sorry about that. Um, but yeah, you can always do some Google search and you will find some or the other good explanation of Dijkstra's algorithm, right? And that should be helpful. Um, if not, you can also post it in the discussion forum if there is a particular step or specific step in the Dijkstra's algorithm that you find a bit difficult to understand or something like that, then you should post that in the discussion forum and that will help Bhaskaran sir, to narrow down your doubt and address it in a precise manner. Okay. Um, so I'm not sure what this particular message means. Segment insertion in B2B estimate cost. I'm not sure what that is. If you could elaborate on that a bit more. I think one of you are speaking, but your voice is very low. Can you maybe try keeping the the mic close to your uh, face? Okay, you can also write it out in the chat box if you are facing some audio issues. That's fine. Okay, in the meantime, um, so that brings us to an end of the question that we were supposed to discuss this week. Um, Basically, we covered branch and bound and A star method. So one of the common variations of A star method is the weighted A star method. Okay, wherein basically, so initially in A star, what you did was you simply defined F to be um, F is equal to G plus H, right? Now you could also assign different weights to the G component and the H component. You could decide to give a higher weightage to the actual cost component. You can also decide to give a higher weight to the estimated cost component. Okay, so that is how you are going to your this variation of weighted A star method is going to differ from the normal A star method. Okay, how to convert a TSP tour cost to graph. Okay, if you're just given the cost, then it's difficult. You also need some kind of map in order to figure out, right? Uh, if you're just given the cost, let's say if you're just given 290 from the A star method, and you don't have any information on the individual segments, then that will be a bit difficult to arrive at. But if you are given some additional information, then you can try to deduce that okay, the distance from this node to this node is this. So you could find out potential edges that you could add up to represent your final optimal tour, and you can see whether that is adding up to your optimal cost that you have. Okay. Well, for this problem, what is the cost of the tour? Can we consider actual and expected cost? So the cost of this tour is 290, and the reason that it is 290 is that when you arrive at um, G node, okay. So remember when you started from your S node, your F was G plus H with G being 0 and H being 160. Okay. This case will reverse when you reach your goal node. Here your F will become G plus H with estimated cost 0 and actual cost 290. The reason behind it is that you would already have found a tour up to or optimal path up to your goal node. So your estimated component would automatically become 0 because there is no further distance to cover from your goal node to the goal node, right? Distance from goal node to goal node is 0. That's why it is okay to call this cost 290 as the optimal cost. Okay, so some of you are asking questions on how to find segments if the tour is given. And uh, So one of the things that just comes to my head is, if you're given a particular tour, you could just look at the individual segments and then analyze them separately, right? I'm not sure about the question exactly. You said that it's given in the practice assignment, so maybe we can just quickly have a look. It's given in the practice assignment. So it must also be given in the solutions, must also be given in the lecture materials, right? So have you explored that? Huh. See, you have different practice assignments, and I'm sure this would have solutions as well. So you can go through this. Okay, Bhaskaran sir has put in quite a lot of effort to prepare these. So once you go through this, there's some issue with the loading of this particular PDF. But if you go through this different practice problems over here, I think your issue will be resolved. Okay, it's not included in the solution. Um, okay, in that case, I would highly encourage you to post it in the discussion forum as soon as possible, because I haven't gone through the practice questions, right? So it would be unfair for me to immediately jump to it and try to solve it. Also, it might have some relation to your actual graded assignment, right? So yeah, post it in the discussion forum maybe right now, right away, and Bhaskaran sir can maybe see it and address it before the final deadline. Okay, so with that, um, if there are no further things, we can end the session now, and we can meet again in the next week. And once again, if there is something in particular very specific that you really want to discuss or have discussed in the next live session, please post it in the discussion forum with a heading that live session request for a particular topic or a particular question. Okay, it will be easier for me to prepare in that way, and also more efficient for us to have these discussions in the coming live sessions. Okay, so with that, let's end the live session. Thank you all for joining, and let's meet next week.